Okay, good morning. By way of clarification, on problem 55, you'll notice that the body text and the figure seem to have a discrepancy on what velocity the flow is, and so please use 5 meters per second as the correct velocity for that problem. Reminder that assignment's due on Tuesday, and today we're going to be talking about rotational flow. So before we get into that, do you have any questions from the previous lecture and the examples we worked on Tuesday, or any questions related to the lab that we did earlier this week? What kind of acceleration were we experiencing with the Venturi? Convective acceleration, which is where there's a velocity change with respect to position, right? So velocity is a vector with two components. It has magnitude and direction. And since the flow was all going in the same direction through that pipe, it was the magnitude of the velocity that was changing. And so Bernoulli's equation is what we use to characterize how pressure is affected by changes to the magnitude in velocity. Today, with rotational flow, we're going to look at what happens when the direction of velocity is changing. When you may have the same magnitude of velocity, but when flow is going in circles, there are some unique characteristics with how the pressure responds to that. So that's kind of the direction that we're headed in. Is, if we think about the filling in the blanks on different types of acceleration and what kind of flow type it's dealing with, we just said that Bernoulli's equation was convective acceleration, and convective acceleration is what we think of as corresponding with non-uniform flow. Non-uniform flow is when the flow conditions are changing with respect to position, whereas unsteady flow is the time component. And so local acceleration is associated with unsteady flow, and then local acceleration is tied with the Euler's equation, which is changes in pressure and elevation due to those. And so today is a new acceleration type, centripetal acceleration. So let's watch a quick video to illustrate this radial acceleration that we're going to be dealing with today. Okay, so radial acceleration. This is an important formula, and it relates the centripetal acceleration, which still has units of meters per second squared, regardless of whether it's local acceleration or convective or centripetal acceleration. We still have units of meters per second squared. And now this omega term is the rate at which it's spinning, and it has units of inverse seconds. And then radius obviously has units of meters, and so that's how this radial acceleration is meters per second squared, is we've got meters in the radius, the distance away from the center line that some particle is, some fluid particle that's spinning. We could measure how far it is from the center point of its rotation, and then inverse seconds is related to how quickly it's spinning. So the tangential velocity would be the speed of some particle. If we multiplied the radius by omega, the angular velocity, then it's actually the magnitude of its velocity, its speed. Of course, its direction is always changing, but at that tip, sometimes there are questions that are talking about what's the actual speed of a fan blade at the outside edge of the tip as it's rotating. And the way that you'd calculate that tangential velocity is you can multiply the radius by the rotation rate, the angular velocity. Now, a lot of times when we're dealing with pumps, the way that the rotational rate of pumps is described would be in revolutions per minute, RPM. But what we need to do when we're doing these centripetal acceleration type problems is our angular velocity should be in terms of radians per second. So each revolution has 2 pi radians, And of course, we know that there are 60 seconds in a minute. So if you want to convert between RPM, which usually is what you'll be given, and radians per second, which is what we need for these radial acceleration type problems, then you'd multiply by 2 pi to get from revolutions to radians, and then you divide by 60 to go from minutes to seconds. So this is a conversion that you should commit to memory. I don't think that that conversion is specifically listed on the equation sheet that you'll get for the second exam, but it's the sort of thing that you could just prove to yourself, or redevelop even if you don't have it memorized, knowing that there's 2 pi radians in a revolution. So the question becomes, when a fluid particle is spinning around in a circle for whatever reason, whether it's water that's in an aquarium that's spinning, or flow around in a vortex like a draining tub, or there are other reasons why fluid goes in circles, like in the outside edge of a pump. When it's going in circles, then how is the pressure affected by that behavior? So here are a couple of illustrations of fluids that are experiencing radial flow. A water vortex, which we'll take another look at one of those in just a minute with the YouTube video, or in a tornado. There are pretty incredible changes in pressure due to tornadoes, and we can use radial acceleration.
Appalachian Power wants to help you.
We'll look at situations where the fluid is open to the atmosphere, and then also cases where it's enclosed. But in both cases, there's a pressure change due to the acceleration. All right, so this is the first case that we're going to look at. This is what's called a U-tube, and these were called U-tubes long before there was YouTube online. This is just basically an open to the atmosphere glass or plastic tube where we're able to see the liquid level inside of here. And the reason why it's shaped the way that it is it's being rotated about one of the legs. And so you can see here this little circular with an arrow mark on the end there. It gives us an idea that it's spinning around. And in problems such as this, it's common to specify the deflection between the left leg, which is right at the axis of rotation, and then we're defining some radius from the center line of rotation out to a point of interest. Now here's the equation that relates rotational flow. And it's important for me to point out that it looks like Bernoulli's equation, at least the first two terms do, but this is not the Bernoulli equation. And I'm always trying to point out these common mistakes that I see semester after semester, hoping that I'll eventually get a group where nobody makes these common mistakes. The common mistake that I see a lot is people forgetting that this third term of the rotational flow equation has a minus sign. It's not a plus. And so with that said, let's look at in more detail what we're looking at here. So we've got pressure head, elevation head, and then some term that says we've got rotational flow, so omega squared times the radius from the center of rotation, so the distance from the axis of rotation. Between 2 points, this equation is going to be relating all three of those terms, and it doesn't matter where the 2 points are. It can be anywhere in the system as long as it's connected by a fluid, and this rotational flow equation will be accurate. Now it has to be the same fluid connecting the 2 points. Like if I had partly oil and partly water in here, I couldn't go from one point to the other. I have to go through one consistent fluid, and then I could solve a multi-fluid problem in steps, just like we did with the hydrostatic equation. But in this case, let's just say, for instance, that we wanted to say location 1 is on the left leg right here, where R1 is going to be 0 because it's right on the axis of rotation. So there's no radius, no distance away from the point about which it's spinning. And we could say that let's have this water level be our elevation datum, so that Z1 is equal to 0. And then what do you suppose we know about the pressure at this interface between the liquid inside of the U-tube and the gas that is open to the atmosphere. Zero pressure. So we're going to say, let's work in gauge here, relative to the atmosphere. And so here at the opening and the interface of the liquid and the gas, the pressure at 1 is 0. And we can make location 2 be this spot where it's the free surface of water. And so the only thing that we don't know, since we have P1 and P2, Z1 and Z2, we know the radiuses. R1 would be 0, R2 is going to be 0.1 meters. The only unknown in this rotational flow equation is how quickly it's spinning that caused this water deflection. And so I'm going to pause the recording for a moment, give you a chance to calculate this, solve for the rotational rate. And I'll point out that all these other variables have like P1, Z1, R1, but there isn't an omega 1 and omega 2. Why is that? Yeah, it's the same physical device, and it doesn't matter what location you're at, it's still rotating at the same number of revolutions per second, or it may have a different tangential velocity, but it doesn't matter where the location is, but since it's one physical piece, it's rotating around at the same rotational rate. So the omega is constant through the whole system. All right, so solve for omega, and then let's go back to this formula for radial acceleration from the previous slide. A sub r is omega squared times r. So the second part of this example asks, what's the radial acceleration experienced in the right leg, and then the tangential velocity in the right leg? And the tangential velocity was E sub t is r times omega. So the key to solving problems like this sometimes is picking the right spot for 1 and 2. And a good rule of thumb is pick spots where you know lots of things. Because, you know, if you have too many unknowns in an equation, then you're not going to be able to solve it. And so here, where do we know a lot of information? Well, we know a lot of information at the interface. What do we know? We know elevations, and we know the pressure, and we also happen to know the radius at both of those points. And so here I kind of told you location 1 will be the left, location 2 will be the right. You know, this equation is valid anywhere. We could say here is 1 and there is 2, but we don't know from the dimension drawing what those radiuses are, and we don't know what the pressure is at those locations. And so sometimes the key to success is picking the right boundaries to apply this equation across. All right, so here I've got all of the variables defined. P1 is 0, radius 1 is 0, pressure 2 is 0, Z1 is 0, Z2 is 0.25. We end up canceling out most of the terms of this rotational flow equation, all of them on the left-hand side. And so what it ends up being is that if we rearrange it, the rotational rate is 22.15 radians per second. And then if we convert that from radians per second into revolutions per minute. And then we have to multiply by 60 to go from seconds to minutes, and then divide by 2 pi to go from radians to revolutions. So it's the inverse of that conversion that I showed you on the previous slide, since we're going from radians per second into RPM. So how many people got 211.5 RPM? Very good. You know, this units of radians per second is kind of interesting because we kind of treat radians like it's not a thing when we're looking at the units associated with acceleration. Because remember, we're going to have omega squared times r (49.05 meters per second squared). But we didn't say 49.05 radians squared meters per second squared. It's just sort of like the radians evaporate. It's no longer a thing again when we multiply it by the distance. I'm not sure why, but that's how it works. 49.05. Sometimes these problems in the book ask you to express the acceleration in terms of g. And so here's the acceleration in terms of meters per second squared. But if it said how many g's is it in the right leg, then what we could do is just divide by 9.81. So 49.05 meters per second squared divided by 9.81 meters per second squared per g. So that's 5 g's. Remember we watched the brief video of a pilot who was spinning around in circles to simulate acceleration. He was trying not to black out, kind of like flexing his stomach muscles to prevent the blood from draining from his brain. So you can calculate how much g's would be experienced by rotational rate and the radius away from that center point about which it's rotating. Any questions so far on the first two components of that example? All right, finally the tangential velocity, 2.215 meters per second. Everybody get that same value there? Great. All right. So that's our first example. This is also a YouTube, but we're taking this up to the next level. So some differences here. First of all, it's not open to the atmosphere. So we've enclosed the tube, and what that means is that the fluid is restricted from sloshing around and changing its location as the U-tube is spinning. Now, just because its physical location can't change, that doesn't mean that the pressure is held constant. The pressure will change. The next thing that we've done to complicate things a bit more is that the axis of rotation isn't in one of the legs. It's not that complicated. All you have to do is just measure the distance from the center line of rotation to the points of interest. And our 2 points of interest are L and M. And we aren't given any sort of absolute elevation measurement for L and M, but we do know the distance between them. And so a pretty common practice would be just to select the lower of the two, let that be z equals 0, and then the higher of the two, in this case M, is just going to be 0.125 meters as the z2. All right, so the rotational rate here is given, and we want to know how is the pressure changing inside of this tube between L and M. We know the pressure at L, and note the tube is filled with an oil that has a specific gravity of 0.85. So the fluid properties are important here in the pressure head term where we've got the gamma. So we won't be using a gamma of 9810. Instead, we'll have to calculate the gamma for the oil. And then the other trick that I'll point out is the rotational rate here is given in terms of RPM. And in this equation, we always want to use radians per second. Okay, so again, I'm going to pause and I'm going to ask you to tell me What is the pressure at M? Conditions are not static. The pressure change is going to be explained by this rotational flow equation. Even before we start plugging numbers into the equation, we can just by inspection have an idea of whether the pressure is going to be higher or lower. So consider the difference between L and M. Now, the hydrostatic effect is still there when the fluid is rotating, and the equation accounts for that. In the same way that, remember, I told you that Euler's equation automatically accounts for differences in elevation, even though it's also going to keep track of any additional acceleration. It's also handling the gravitational acceleration, the pressure changes that comes from that. So consider L and M. M is higher. So that means the pressure at M should be lower. And now consider the radiuses, because that's the other factor, is how far they are from the center point. The one that's further away is going to have more pressure, like further away from the axis of rotation, and L is further than M. So on both of those accounts, the elevation factor and also the distance from the center point of rotation, that means L has a higher pressure than M. So whatever we end up calculating through our rearranging the formula and substituting things in, you may want to double check the answer and make sure if it seems reasonable compared to the starting point. All right, so with that in mind, we get some of these preliminaries out of the way. You develop a little sketch, identify the variables where we have given information, calculating our new unit weight based on the specific gravity that's specified for the oil in this U-tube, doing the conversion from RPM to radians per second. You know, if I was looking at an exam problem and all you did was a sketch and identify the variables and a couple of these beginning conversions, that may be 3 or 4 points out of 10 right there. Just having the reflex to start setting things up in an organized way. I think there's a lot of value in that. But the chances are, even if all you can do is a sketch and some of the preliminary stuff, once you start the problem, even if you're stumped, sometimes it'll dislodge a memory on similar problems you've seen in the past. And from the last exam, I think every one of those problems so closely related to a homework problem that you'd been assigned previously that if you start down a path, you'll maybe recognize where you've done it before. So here, we just do some algebraic rearrangement to isolate the unknown variable P sub m, the pressure at M, that right leg that's elevated. And you'll notice here that I've done it in steps, mainly so that it's easier for me to check my work that second and third time. I don't want to lose any points because I forgot to square something. So if you show it in groups and then you can double check later on, so you can see where all of the different pressure elements are coming from. What's adding to the pressure, what's causing a pressure decrease, and in the end, you should get that the pressure at M is 1.34 kilonewtons per meter squared, or 1339 newtons per meter squared. Anybody else get that same value? Okay, good. I'll leave that up for a minute in case you need to write anything down here. let's play some what-if games. Those are always fun, right? All right, so what if we made the right leg longer? What would happen to the pressure at M? It would increase, right? Because the further away it is from the axis of rotation, that's going to increase the pressure. Because what that would be doing effectively is it'd be increasing the acceleration. Even if it's spinning at the same rate, there's more acceleration when it's further away from the center point about which it's rotating. What if we change the fluid from this oil to mercury? Well, in that case, then the pressure changes would be more severe as we have differences in elevation or differences in how far away they are from the axis of rotation. So if we had held this pressure at L, if it was still the pressure at L is 2.75 kilopascals, if this had mercury in it, then the pressure at M, the pressure difference would be so great that actually it would, if I was setting up a problem like this, it would maybe go negative because 12 centimeters of mercury is going to have a big decrease in pressure. So the reason why I ask the sort of what-if scenarios is here we have a problem where what we're looking at, these dimensions are given before it starts to rotate. And then we start to rotate at 8 radians per second, and the question asks, find the equilibrium water elevations. And so in the last problem, we were solving what is the pressure. Here the unknown is what are the z's. Now, what is z1, what is z2 when this begins to spin? So there's two unknowns, actually. When it begins to spin, the water's going to go down on one side and up on the other. Anybody want to take a guess on which side the water level goes down on? That is correct. It goes down on the left. How did you know? Shorter radius, less acceleration. Those are both interrelated. So what we're going to do is apply this equation, the rotational flow equation. So when it starts to spin at 8 radians per second, there's going to be some difference in elevation. How do we know where to apply the equation? In other words, where should be 1 and where should be 2? What's the rule of thumb that I told you earlier today? Yeah. More broadly, yeah, so that's what, let's do that. This is 1 and this is 2. But like if we speak even more broadly, pick locations where you know things, right? And we know that the pressure at the interface of, it's an open gas, because both of these are open to the atmosphere. It's air and air. So we know that P1 is 0 and P2 is 0. Okay, so that's going to make 2 of the terms in this equation cancel out. Omega is given in the drawing, 8 radians per second. What about the R values? Okay, those are also given. The only thing we'll have to remember there is to convert from centimeters to meters, so that's pretty easy to do. It says in the problem statement, find the equilibrium water elevations, and so the gamma we can know because it mentioned this was water. But there's a trick here. We've got Z1 and Z2, and we don't know either of them. And this equation, we've just got the one equation. So how are we going to get around this? How are we going to solve the equation when there's 2 unknowns? What's that? Set 2. And what's your rationale? So he's saying set Z1 equal to 2Z2? I see what you're saying. That's a good guess as any, but I think it ends up not being true. Because remember, the radius is squared. So his rationale was maybe look at the the radiuses, and then you could tell where the elevations are based on that. That is not the case.
Should we eliminate one of the arms and have it where one of them would be pressure of 0, radius of 0?
Okay, that's a great question. He's saying, well, what if we just had one of the radiuses be 0? So we can't move where it's rotating about. Like, the system is rotating at this location. And besides, we know R1 and R2, so the R values aren't, that's not the information that we're lacking. It's the elevation that we've got too many unknowns on.
You just set where your P1 is, that's going to be your datum.
Okay.
P1 is.
So you're going to say, let this be the elevation datum. Okay, so Z1 is equal to 0.
You just have that.
Then Z2 is going to be an unknown.
And once you get to your delta Z,
Yeah, so how do we get the delta Z? Delta Z is basically Z2 minus Z1, right?
yeah, so you could manipulate the equation through Z2 minus Z1, solve for what that equals to, and then add it to where it is initially. Well,
We need another equation. We need an equation that relates Z1 and Z2. And I'll give you a hint. The amount of water inside of that U-tube isn't going to change when it's spinning. It's just going to be in different locations. And so here's the before. In the before, there's 18 centimeters in the left side, and there's 18 centimeters on the right side. So when it's spinning, there's still going to be 36 centimeters of water. It's just some of it's going to be on the left and some of it's going to be on the right. And so that's where we can get another equation from. What we can say is Z1 plus Z2 is equal to 0.36 meters. So let's have the elevation datum be the bottom of this tube. And doing it this way, by saying Z1 plus Z2 is equal to 0.36, now we've got two equations, two unknowns. Before we just had one equation and two unknowns. Both of the elevations weren't known. But basically what this means is, another way of putting it is, if the water goes down 1 centimeter on the left, that water has to go up 1 centimeter on the right, as long as the diameter of this tube is the same. You know, it would be altogether different, like if the left leg was a smaller diameter tube than the other one. Then we'd have to look at the ratio of the areas to know how the Z's were related. But does everyone get that idea that if we're spinning it around such that it went down a little bit on one side, it's going to have to go up the same amount on the right? There's conservation of volume of water. It's just its location changed. Okay, so find the equilibrium water elevations, and you can use this rotational flow equation and then this equation that I've just written on the board, Z1 plus Z2 equals to 0.36 meters, to find out when it's spinning at this speed, where are the water elevations at? You know, what is Z1 and what is Z2? Really don't have any of those tools. All right. So the Z2 would be 0.3385. That's the elevation on the right. And the elevation on the left would be 0.0215 meters. So let me write that on here. Z2 is 0.0215 0.3385 meters. C1. Did most of you get something relatively close, depending on how many digits and round off and all that sort of thing? You may have got, 0.34 and 0.02, and that's okay. It seems like, as I was circulating around, most people had the right answer there. That's what happens that when it's in equilibrium at 8 radians per second. Now think about, physically, the system. What happens as we speed it up and slow it down? It's only got 2 centimeters of water when it's spinning 8. What happens if you actually just plug the new rotational rate into the equation? Here was the equation that we had. Z2 is 8 radians per second squared divided by 2g, so 9.81 meters per second squared. And then that's multiplied by 0.18 meters squared minus 0.36 meters squared minus 0.36 meters divided by -2. Now, yours may look different depending on when you started doing your substitutions into the algebraic equation. I did mine all at the very end. So this is where we got this Z2 is 0.3385 meters. So Z1, okay. So if 8 goes to 14, then what that would do is it would increase your Z2 even more, such that when you put it into Z1 plus Z2 is equal to 0.36, what did you get for Z1? Some negative number, right? Well, that's not possible. The water, if we're saying that this bottom leg is our elevation datum, the Z2 can't be negative. The water can't go below the outside boundary of that tube. So where's the water going instead? When we start to spin it, it's got 2 centimeters, then it's got 1 centimeter, now it's at 0. So where's that water level going as we continue to speed it up even faster? It's horizontally now. So now the water boundary is, I'm tempted. No, I'm not going to do it. I wonder if it would come off, though. I mean, it is. Doesn't? We'll see about that. I just did that mark. If it's here next week, then we'll know. All right. Don't tell it was me, all right? A secret is safe with 48 people on the internet. I'll never get in trouble. Yeah. All right. Okay, so it doesn't work anymore, right? We're spinning it too fast. So that negative value is nonsense. So what's the solution? It's no longer true that Z1 and Z2 are 0.36. That's not true anymore. Once we've got the water level in this leg, then the total sum of liquid in the right leg is more than 0.36. Because we've got all of the water from here is there, and a little more. So what we would have to do instead is we would have to come up with an equation that relates R1 and Z2. So then that would be our 2 equations and 2 unknowns. Is we wouldn't exactly know where the interface is. We'd say, we do know the Z value at least, right? We'd say location 1 is here. So tempted. Right there is Z1. Here is Z2. And so we know the elevation value, but the radius is unknown. So now what we would say is Z2 is 0.36 plus the R1. So if R1 is any less than 18, then it gets additional inches, right? So how would we say that? What would the equation be? 18 minus R1? Come on, help me out, guys. I'm standing up here improvising this. we're saying that for every centimeter that it goes into this bottom leg, it's going to decrease the R1, but it's going to increase the elevation. So another way of saying it is R1 is 18 minus whatever the z's are. It's not coming to me right now. I shouldn't improvise. But you get the idea. The idea is that we'd say this equation is no longer valid, the two elevations, and instead what we'd have to do is start relating the location in the base leg with the increased elevation. So, all right, let's take a look at these announcements and figure out where we're at. On Tuesday, you've got this big assignment due. My office hours are always a ghost town. Nobody comes to visit me. I'm up on the 3rd floor, and I understand that you don't want to climb up those stairs, but there is an elevator. So if you've got questions on the homework, don't leave it till Monday night to start thinking about it. Come see me, and I'd be happy to help you out. Or if you want to send me an email over the weekend, I'll do my best to respond. Remember, this is the crest of the course. Chapter 4 is so important, so don't let this be one of the ones that you skip. Turn this one in. It's important. I'll see you Tuesday.